Greetings, my name is Professor Stephen Roman. A few years ago, I did a series of YouTube lectures on category theory that were fairly well received, judging by the comments. And so I was encouraged to do some additional videos. I did, I think, 6 videos on group theory, which I intend to redo because I'm not real happy with them. But more recently, this is now July of 2020, I was teaching a transition to advanced mathematics course, and I did a series of video lectures for that course. There are 23 lectures in that series, and I may add another lecture, make it 24, I'm not sure. In any case, I have decided to continue to do lectures on YouTube. I have just finished a 3-volume series called Abstract Algebra: A Comprehensive Introduction. There are 3 volumes to the series. The first volume is linear algebra, and as soon as I find the right page, here we go. The second volume is group theory, and the third volume is ring and field theory, and I'm contemplating adding a 4th volume on the theory of order, lattices and order. These books are designed for the serious undergraduate or beginning graduate student. My intention is to do video lectures for all 3 books. It's going to take a while. As far as the dependencies on these 3 volumes, linear algebra can be read independently of the other volumes, and so can group theory, but ring and field theory does reference material on both linear algebra and group theory. But any reader with a modest acquaintance of these subjects can read the 3rd volume without reading the first 2. I'm going to make the 3 volumes available for purchase on my website, and it'll be in PDF format, probably. And so this video is sort of an introduction to the series and then to this particular volume 1 on linear algebra. As the title suggests, this series is a comprehensive introduction to abstract algebra, where by introduction I mean that the book starts more or less at the beginning, and it assumes no prior knowledge of abstract algebra. The only prerequisite really for this series is an understanding of the basic mathematical tools that you would find in a transition course that are covered in my lectures on transition, and a solid understanding of elementary linear algebra as would be taught in a relatively serious lower division course. I think that first linear algebra course is probably one of the most important courses that a math major certainly will take, because it does, or I think should provide, an introduction to abstract mathematics as opposed to calculus. Unfortunately, I find that sometimes that course is so watered down that it doesn't really give the sense that one gets from a non-calculus mathematics course. I always try to add a few topics to the course when I teach it, just to make it seem more like what you might call a serious math course. That goes over well with some students, with many students, but there are also many who dislike that. Of course, any other experience with math courses would be of help, no doubt, just in the sense of experience, mathematical maturity, or however you want to say it. I realize that this may be a first exposure to rigorous abstract mathematics for some readers of the book or viewers of the lectures. So I've tried to write my discussions and proofs with an eye towards developing sound mathematical thinking patterns. So each proof should be thought of as not only a mini lecture in mathematics in the content, but also in writing style and proofwriting in general. So I would urge you to think, when you read each proof, not just about the mathematics, but take a minute or so and read over the proof with the sense, from the point of view of the mathematical style. I'm not suggesting that my style is better than anyone else's, and certainly it's not the only style that would be considered good style, but I have had 50 years of experience teaching mathematics, over 9,000 lectures, and also I've written 30 books in mathematics and 10 books in computer programming. So I have, if not much talent, at least quite a lot of experience in mathematical exposition. It's true, and I think you may know this yourself, that proofs in most books are not always written to show the thought pattern behind the proof, often preferring elegance or conciseness over insight or motivation. But I think showing a bit of motivation behind the proof is extremely valuable for students. Of course, it's possible to get carried away with this idea, so I've tried to temper it with an eye towards not bloating the text. But I do think it's important. By comprehensive in the title of these books, I mean that the books in this series include a somewhat wider range of topics. Some are marked optional, others are not, and some are placed in topics chapters. But there are more topics, I think, than is often seen in elementary, undergraduate treatments. And so hopefully all readers will find something of interest in these books. My goal is for all readers to leave the series with a thorough grounding in the fundamentals of abstract algebra, well prepared to attack more advanced treatments if desired. It seems also that the current trend in mathematical education is to motivate abstract concepts by introducing applications as quickly as possible in an effort, I guess, to satisfy those students whose overriding question is, of what use is this material? And while I certainly respect the views of those whose main concern is whether or not the material at hand has applications to the real world, I've chosen to take a more abstract approach to the subject. I'm a pure mathematician, and I do appreciate mathematics as a pure art form, as well as the cornerstone of all science and technology. I checked the dictionary for the term art, and it says something that is created with imagination and skill, and that is beautiful or that expresses important ideas or feelings. I don't think anything could possibly fit this description more accurately than mathematics, and in particular, abstract algebra, as well as other branches, of course. This isn't to slight any other art forms. I'm a huge fan of classical music and painting and other art forms. But mathematics has a rather special position among all art forms, I think. It's certainly not to everyone's taste. In fact, I guess to relatively few people's taste. But hopefully it's to your taste, or you wouldn't be listening to this video. As to the volume on linear algebra, the subject of this particular lecture series, this is a comprehensive introduction to linear algebra designed for the serious undergraduate or beginning graduate student. And as I said a little while ago, the prerequisites are a typical transition course and a moderately serious, should we say, lower division linear algebra course. The following topics you should be familiar with before proceeding into this book. Proof techniques, such as proof by contradiction, proof by contraposition, proof by induction, the arithmetic of complex numbers, the algebra of polynomials, equivalence relations and partitions, which I review quickly in Chapter 0, but I probably won't devote a lecture to, because it's part of a transition course and you can certainly read the material on your own or Google it and find what you need to know. The basic properties of matrices and determinants, such as row and column spaces of a matrix, the rank of a matrix, elementary matrices, Gaussian and Gauss-Jordan elimination, that sort of thing, and finite dimensional Euclidean space Rn. As to the organization of the book, and therefore the lectures, the first chapter in the book, Chapter 0, is entitled Preliminaries and is divided into 4 parts: background material, matrices, equivalence relations and partitions, and canonical forms and invariants. And while much of this material may be familiar to you, there is probably material that is not familiar. And so I strongly encourage everyone to either read this chapter or go through the lectures. As I said, I'll probably skip some of the material because it's something you should have seen before, but there's going to be some stuff that we need to talk about, such as block matrix algebra and a few definitions related to matrices, quasi-diagonal matrices, for example, and discussion of canonical forms and invariants for equivalence relations that I'm guessing you haven't seen before. The rest of the book is divided into 4 parts: the basic theory, inner product spaces, spectral theory and canonical forms, and then topics. And there are a couple of appendices too. I don't think I'm going to go through the preface here in detail and outline the content of the book, because Generally speaking, that this portion of a preface, I think, is written for the professor, for someone who's thinking about adopting the book for a class. If I said to you, for example, we're going to discuss normal, self-adjoint, and unitary operators in Chapter 8, that probably wouldn't mean a whole lot to you at this point. I will go over the table of contents with you very briefly so you'll get a sense of the breadth of coverage, but I don't want to dwell on that too much. There are some important appendices in this book on cardinality, on partially ordered sets, and on Zorn's lemma, and we probably will need to go over those at the appropriate time. I would, however, like to make a few remarks for those of you who are beginning this course or beginning a study of abstract mathematics. To study abstract math, one needs to begin to think at least a little bit like a mathematician. But what does that mean? Well, who knows really? I mean, it's difficult to put in words. But there are a few aspects of thinking like a mathematician that I can put in words, and that I suspect with which few mathematicians would disagree. I'm sure there are a lot of opinions about what it's like to think like a mathematician, and I won't even try to be comprehensive about that. However, this is what my advice would be as you read the book, as you listen to the lectures. And it's a little more difficult as you're listening because it's a little harder to pause and start again, but I think that's something you should want to do probably quite often. Stop the videos as you're watching them, spend a minute or two thinking about something, then restart, and then continue with the video. As you read and think about mathematics, you should always and repeatedly ask yourself the following question: how do I know this is true? Every time you read a sentence that's not crystal clear to you, ask yourself, why is this true? How do I know this is true? You should be asking this question a great many times, even several times per paragraph if the going gets tough. That's what I do when I'm reading research papers or advanced books. It's slow going. They do not read like novels. Math books don't even read like history books or many other academic subjects. One needs to stop frequently and think. Also, to help answer these questions, you can ask another question. How else can I say this? How can I rephrase this? To what is this equivalent? It's surprising how often just rephrasing a mathematical statement in a different way will set a light off in your head and allow you to understand what the meaning of the sentence. It's just everyone's brain is different, and I can go into a class and I can say something and I can see several people with puzzled looks, and so I will rephrase exactly what I just said in a different language, and the light will go on for some of those students. That's just the way it is. Everybody absorbs information, especially highly technical information, in a different way. Of course, to be successful at doing this, you must know the terminology the definitions, because they are the key to finding other ways to say things. Finally, in order to be successful as a student of mathematics, you must commit to memory all definitions and statements of theorems as they appear. I know students don't like to hear this, and they take offense at the idea that they have to, many of them, they have to memorize definitions. I'm sorry, that's just the way it is. When you study a foreign language, you have to memorize the vocabulary. In a way, mathematics is a foreign language. And so the definitions must be learned and must be learned quickly before moving on. The definitions and the statements of theorems are the tools by which you construct valid mathematical arguments, in other words, proofs. So that's just the reality of the situation. Okay, let's take a quick look at the table of contents for the linear algebra book. This is the preliminary chapter, as I said before: background material, matrices, equivalence relations, partitions, canonical forms, and invariants. Part 1 is the basic theory. Chapter 1, vector spaces. This is mostly traditional material. I think you find these topics in virtually all linear algebra books at this level, but there's a little bit more depth than you might find in undergraduate texts here. For example, a proof that all non-trivial vector spaces have a basis, which requires Zorn's lemma, and a few other things that you might not see in a typical undergraduate linear algebra course. Chapter 2 is on linear transformations, and I take what I hope is a very comprehensive, careful look at issues that give students problems, such as change of coordinate systems or change of representation for linear transformations. So you'll find a few theorems, largely a point of view that you may not have seen before, even if you've had exposure to this level of linear algebra. And I do talk at this point about invariant subspaces and reductions of an operator. These are important concepts in the understanding of canonical forms. Second part, chapter 3, is the second part of linear transformations. Linear functionals and dual spaces, annihilators, dual maps, and these three topics can be covered, and one could skip the remaining topics, or one could cover quotient spaces, correspondence theorem, and isomorphism theorems, and gloss over the first three. So this is almost like a two-part chapter. I contemplated actually splitting it into two chapters, but frankly that's a lot of work, and I'm not sure it's that important. This is material that you would generally not find in my experience anyway, in an undergraduate linear algebra course. Maybe a little bit, certainly linear functionals, but dual spaces and dual maps and quotient spaces and these theorems, probably not so. One of the issues, of course, is that traditional courses are limited in time, 10 weeks at the University of California, and 30 lectures, so one has to pick and choose quite a lot. advantage of doing YouTube lectures is that I can cover all the material, and I don't have to worry that I'm constrained to 30 lectures. Chapter 4 is on eigenvalues and eigenvectors. The second part of the course is inner product spaces. Most of this is pretty standard material, but in a bit more depth, I think, than you would normally find. Again, because of time constraints in a traditional class. Although Chapter 6 on inner product spaces, this material probably would not be covered anyway. The Riesz representation theorem, an operator, the adjoints of an operator. Part 3 is spectral theory and canonical forms. Begins to get a little more abstract, a little more advanced at this level. My approach to canonical forms, the one I've always favored, the one I used in my graduate textbook on linear, called Advanced Linear Algebra, published by Springer in the GTM series, is to use modules, but only what I call operator modules, one specific type of module. So I introduce operator modules right away, and then minimal polynomials and primary decomposition of an operator module. And from there one can prove the very famous Cayley-Hamilton theorem of linear algebra. Then we can get into a serious look at the two of the really major theorems in linear algebra, Schur's theorem and the spectral theorem. And finally, study of canonical forms, including the rational canonical form and the Jordan canonical form. There's a brief mention of the Smith normal form as well, and examples of how that's used. Part 4 is a topics chapter. This is material, some of which can be inserted at various points earlier in the book, others of which come later. For example, uniqueness of reduced row echelon form. This is a topic that I think probably may get mentioned in a freshman or sophomore level linear algebra course. Professor might say, reduced row echelon form is unique, row echelon form is not unique. But the actual proof is a little bit hard to find, so I've given a proof here of that, of the uniqueness of reduced row echelon form. There's also a topics chapter on determinants, which goes through the 3 different definitions of determinant, the common definitions. One uses permutations, one is in terms of multilinear forms, and the final one, the cofactor definition, is the one that you would see in a freshman, sophomore level course in linear algebra. But I give all 3 definitions, and I prove that they're all equivalent. LDU factorization. There are 3 extremely important matrix factorizations that I discuss in this book, various places, and this is one of them, the LU and the LDU factorizations. Polar and singular value decompositions, an introduction to tensor products. A lot of students want to know what these are. I have students in linear algebra asking me all the time, what's a tensor product? And unfortunately, in a traditional class, there's no time to discuss that, but there is a chapter, a topics chapter in this course on tensor products. And the final topics chapter is on modules. So, as I said before, I do use operator modules in the text proper, but only really the definition. It doesn't go much beyond the definition and the concept of a submodule of an operator module. But for those who are interested, this is only 6 pages or so, discussing modules in general, and in particular with emphasis on why they're not as nice as vector spaces. So I call this the vector space appreciation chapter. In a way, it's too bad I can't do this chapter first at the very beginning of the course, because then as you study vector spaces, you'll be saying, gee, these are nice, especially compared to modules. But it's not really, I think, an appropriate organization, or at least certainly not traditional organization. And as I mentioned before, some appendices, cardinality, partially ordered sets, Zorn's lemma in particular, which we use, I think, about 3 times in the course. So it's not pervasive in this course, but Zorn's lemma is really not that difficult to understand, and so it's definitely worth going through.